So before I talked about some principles and then where atmospheres and oceans come from, and now I'm going to talk about what happens to them. So climate evolution, and in particular I'm going to focus on rocky planets because these are the ones we care about most for life. So this lecture has three parts. The first is to do with climate evolution, and I'll talk initially about the effect of life on atmospheric composition. So the first life would have been simple, so microbes. Microbes have metabolisms, and in a metabolism you extract material from your surroundings and maybe you excrete some other material, which could be a gas. And so you can take in gases and you can give out gases. So you're going to change the atmospheric composition. Now there are some bodies that we see that have no atmosphere because they have lost an atmosphere if they had one initially. And then there are other bodies, Venus for example, that has changed, but partly because, even though it has a very thick atmosphere, it's partly related to atmospheric escape. This is when a gas becomes gravitationally unbound and goes off into interplanetary space, never to come back. And then when we're talking about habitability of planets, this is related to the atmosphere through the greenhouse effect. How does this maintain a habitable climate on the Earth? What went wrong on Venus? I talked about the runaway greenhouse for the very earliest atmosphere of the Earth, but this is what we think happened to Venus. And then Mars also has some problems for a habitable climate, partly because of atmospheric loss, but also because of the way that it lacks an ability to recycle the volatiles. So we can ask this question, why are neighboring atmospheres of Earth, Mars and Venus so different? And in a way, our atmospheres are relicts. So if you go to Europe, you see medieval ruins. There was once a castle, but then something got lost or decayed. And atmospheres are a bit like that, particularly the atmosphere of Mars. It's like a medieval ruin, we think. So it may have been thicker in the past. The atmosphere of Venus may have been different and more habitable in the past. But it's different now, so it's changed. And we see something that is a result of partly atmospheric loss on both of those planets. Of course, it's like planets, whether a planet is habitable is also like selling a house. In English we say location, location, location. That's the important thing for selling a house, and it's also important for habitability. And the Earth happens to be in the right position in the solar system, where the incoming sunlight is not so large that it can cause something like a runaway greenhouse effect, at least after the atmosphere and ocean is formed. But this is not the case for Venus. And Mars, it's an issue of the position in the solar system, the orbit, but also the size of the planet. Mars is half the diameter of the Earth, roughly, and it's about 1/9 the mass of the Earth. So it's more prone to lose an atmosphere through processes of thermal escape that I talked about, I mentioned, and also atmospheric erosion. When something hits Mars, an asteroid vaporizes, imparts energy to the gases, and they can attain escape velocity. But also the planet has cooled more quickly, and so it has limited recycling. It doesn't have plate tectonics. But I'll come back to these issues. The questions we want to ask: how did atmospheric composition evolve on these planets? How does that affect the climates? So in other words, the surface temperature. When we think about climate, the simplest parameter is the average temperature on the planet. For the Earth, that's about 15, maybe 16 degrees Celsius now. For Mars, something like minus 55, minus 56 degrees Celsius. That's about the same temperature as the interior of Antarctica. And for Venus, it's 460 degrees, roughly, Celsius. We can ask, have atmospheric gases escaped? Have they escaped from the Earth? Are they escaping from the Earth? What's been lost into space, and what's been lost into the solid planet? So there's two ways to be lost, from the top or from the bottom. But let's talk about a habitable planet, the Earth. And at some point, life originated, probably in the eon of Earth history we call the Hadean. And once life originated, we know that there's the microbes on Earth interact with the atmosphere today. There are microbes that produce methane. There are microbes and plants and algae that produce oxygen. There are microbes that fix nitrogen. They extract nitrogen from the air, turn it into ammonium, and then it goes into living matter, the tissue, into the proteins, into the genetic molecules, the nucleic acids. Those all have nitrogen. It's essential. And when we consider any gas in the atmosphere, you could write an equation. You could say that the rate of change of the concentration of the gas with time equals some source flux minus some sink flux. And it will reach an equilibrium. At equilibrium, there's no change. This is 0, so then the source equals the sink. And one of these, well, the sink term often is a function of the concentration of the gas. And so if you know the source and you have some knowledge of how this depends on this concentration of the gas, you could solve the equation for the concentration of the gas. In a photochemical model, we have lots of these equations for each gas, simultaneous equations. If you're just considering the air in short time scales, then these will be chemistry equations for sources and sinks of molecules. And we solve all those equations together as a function of altitude in one dimension. And that gives us a photochemical solution. But you could do it in 2 dimensions or 3 dimensions. If you solve them like this, you're solving what we call a steady state solution, where nothing's varying. But you could also have a time-dependent model, which is more complicated, and see how things evolve in time. The prebiotic atmosphere before life, there's no oxygenic photosynthesis. Oxygenic photosynthesis, there's different kinds of photosynthesis. Oxygenic photosynthesis is the sort that we're most familiar with that produces oxygen. And before that, metabolism, the source of oxygen is extremely small. The source is photolysis, the breakdown of water molecules, vapor in the atmosphere, in the upper atmosphere. And then it's determined by the rate that the hydrogen escapes to space. Because if the hydrogen doesn't escape, then it can recombine with the oxygen to make water. So it's actually the net production of oxygen is set by the escape rate of hydrogen to space. But even if you produce oxygen like that, abiotically, it can react with chemically reducing gases, hydrogen, carbon monoxide, things that we know come out of volcanoes, even in small quantities, will just eat up the oxygen. And so you end up with a very small amount. This would be the surface pressure. When a constituent is a trace constituent like this, it's not very well mixed, so it'll be very variable as a function of altitude. What was the nitrogen? Well, we don't know what it was before life developed, but probably high, because nitrogen is a volatile. It makes nitrogen gas. The nitrogen gas molecule is quite a stable molecule because it has a triple, it looks like this with the bonding. Triple bond, hard to break once it forms. Nitrogen comes out mainly as from volcanoes as N2 and stays in the air. It can end up in minerals, but what helps that is if biology starts to fix the nitrogen. Once you have nitrogen fixation, biology can do that, then you can return the N from the air into the crust and mantle, because you make ammonium ions, NH4 plus, and that ion can go into minerals and into the crust and the mantle. What was carbon dioxide? Probably higher in the prebiotic atmosphere. There was more volcanism on the early Earth. The Earth's interior was hotter because things like potassium, radioactive uranium, there was more of that. It had not yet decayed, so it's decaying at a faster rate. Hotter mantle, more volcanism, more carbon dioxide. Perhaps it was a few tenths of a bar. It will be removed because it's soluble in rain, and it will react with rocks, and it can react in the ocean. So if it dissolves in the ocean water goes through the seafloor, it can also be removed. Hydrogen, it's difficult to build up a lot of hydrogen because hydrogen is the lightest gas and it can escape from the Earth. It escapes today. The rate is slow. The rate today is about 3 kilograms of hydrogen per second, which is very small. And basically, if we plot something like this on a diagram, we can imagine some input flux of carbon dioxide, which is just a value that it is for volcanoes. Metamorphism is when you heat up and pressurize rocks. You don't melt them, but they can give off carbon dioxide. And then there'll be some sink, which usually depends on how much. The more carbon dioxide, the faster probably the loss. And where these lines cross, that's the equilibrium solution for the CO2 mixing ratio. So if you make an estimate of the volcanic flux, you make an estimate of how quickly carbon dioxide is removed by weathering on the land and at the bottom of the ocean, then you can make an estimate. And it could be several tenths of a bar, maybe it could be more, depending on what you think about where this curve should be, which is not exactly well known. In the case of hydrogen, the loss is escape to space, which is roughly linear with the total amount of hydrogen in the upper atmosphere. And the source on the prebiotic atmosphere, volcanoes and crust, then it gets photolized, the hydrogen escapes from the upper atmosphere, and the source equals sink. Maybe it could give you 1%. There's some papers in the literature suggesting that there are certain ways that this may have been slowed down if the atmosphere was very cold, but it's hard for small planets, the Earth fairly small, to hold on to the hydrogen. And abiotic production of oxygen is from water vapor photolysis and loss of the hydrogen, and then the OH can break up, it can make molecular oxygen if the hydrogen escapes, otherwise this can go backwards. But there's also volcanic gas, and the hydrogen can react with this oxygen and cancel it out, turn it back into water. And the result is this very small abiotic oxygen flux. Now, there might be some very strange cases where you could build up abiotic oxygen, which are discussed in some recent papers in the literature. But on a planet like the Earth, which has active volcanoes, and where the water mainly forms clouds in the lower atmosphere, then the upper atmosphere is quite dry. And so this source of oxygen and hydrogen escape is small. So for example, today the stratosphere has 3 or 4 parts per million of water vapor. Because it's wet here, there's a lot of water vapor at the surface, but it forms clouds. And if it gets colder and colder, you form ice. And so not much of the water that we have in the troposphere makes it into the stratosphere. So it's very dry, so this source of hydrogen is small. And most plausible atmospheres for the early Earth would still have this issue, that the water vapor tends to form clouds. And so the amount going to the upper atmosphere is small. Well, supposing we do this thing again, where we play God and we say, let's make life, let's have a planet with life. What happens? Well, hydrogen for many microbes is food. And the hydrogen can be combined with carbon dioxide to make methane. This is edible. This is still somewhat edible, but less edible. It's like this is something you would like to eat. Maybe not. It's like that vegetable that you leave behind and your mother complains. And then, so hydrogen in the early atmosphere would have been converted once you have methanogens, which do this metabolism, would have been converted to methane. There are other forms of photosynthesis that do not make, they're more primitive, that do not make oxygen. So here's one that uses hydrogen, carbon monoxide, and sunlight, H nu is the energy of a photon, to make organic matter. And this draws down hydrogen, and it's even more efficient because it uses extra energy from sunlight. So once you have anoxygenic photosynthesis, the hydrogen will drop even more. And this organic matter in sediments, or even in the water column, can be converted into methane by a number of different microbes that do fermentation and methanogenesis. So on the early Earth, we imagine microbes living could be on lakes on the land, but also in the sea, and changing the atmospheric composition. Another thing that life does is extracts nitrogen from the air, nitrogen fixation. Today, there are also bacteria that put the nitrogen back. So the process of extracting the nitrogen is called nitrogen fixation. The process of putting the nitrogen back is called denitrification. But today, the denitrification, the bacteria that do this process, they use oxidized intermediates, nitrate, this is nitrate, and this is nitrite. But these are produced from the oxidation of ammonium with all the oxygen we have today on the Earth. So this would have been inefficient on the early Earth. And probably what happened is that nitrogen got extracted from the air, and nitrogen, the partial pressure probably dropped once this metabolism evolved. Some people think that nitrogen was some kind of, the level of it was in some way monotonic, or it hasn't changed very much throughout Earth history. This is probably incorrect. There was probably a lot in the prebiotic atmosphere, maybe 3 bars like on Venus. But once this happened, it would have been returned to the crust and the mantle. And maybe there was lower nitrogen in the Archean than today, perhaps. There's some evidence, which I could talk about the nitrogen levels in the Archean being lower than today. What about oxygen? This is the biggest effect, really. And when we think about the history of the atmosphere from 4.5 billion years ago to today, this is in billions of years ago, it's kind of chopped off. here. There's been big changes in the atmospheric oxygen level. So this is the absolute level in percent, or down here, parts per million, parts per trillion. And like I said, before life appeared, we had extremely low levels of oxygen. This is just a sketch. But by the end of the Archean eon, oxygen was still low. There's evidence that it was below, geochemical evidence, which is a little tricky to explain, but there's geochemical evidence that it was below a part per million. And then what happens is that there's evidence to show from the oxidation of rocks and also certain isotope changes that oxygen rose about 2.4 billion years ago. And it would have been sudden, probably, because the atmosphere is a small reservoir geochemically. And if you have an imbalance where the source flux is bigger than the sink flux, the atmosphere can quickly change. When this is not a zero, you have this d by dt is active, and the gas concentration can quickly go up.
Then the sky began, the sky was red, then became blue.
The twilight sky was yellow. Well, we don't know really. It depends on the other particles in the atmosphere. So in this part of the atmosphere, methane was probably high, because today the methane reacts with the oxygen and gets destroyed, and we have a lot of oxygen, 21%. This had hardly any oxygen, so the methane could last much longer and build up to higher levels. And when you have this, you can have what happens on Titan. You can have a haze of hydrocarbons. And so that could have changed the sky color. But then when oxygen rose, this would have gone down and the sky would have cleared and would have become blue. And there's also an ozone layer, so even the twilight sky is not yellow, it's now blue. There's some evidence that oxygen did a kind of overshoot, like sometimes when you have a bad thermostat in a house or a room, and it overshoots. But then there's this period of Earth history here from about 2 billion years ago, or 1.8 billion years ago, to 0.8 billion years ago, a whole billion years when not much happens. And geologists call this billion years from 1.8 billion years ago to 0.8 billion years ago the boring billion of Earth history. And it's so boring that I changed it. I cut it there. And the reason it's considered to be a bit boring is because there's no evidence of glaciation from this period that's reliable. It looks like the Earth didn't have any glaciation, which is unusual. So warm for a long time, a billion years. And life did a few things. Green algae appeared, red algae appeared. Red algae, we use them today for sushi. Nori is a type of red algae you wrap sushi in, and you can use it for thickener in soups and things. So red algae appeared. And maybe this says something about geologists, but red algae have male and female, so sex appeared in the boring billion. So it wasn't altogether boring, if you like algae. And then, about 600 million years ago, there was another rise of oxygen. Now look, I put these snowflakes here because these are periods when there are big glaciations. So when oxygen goes up here, it knocks out a greenhouse gas, knocks it down. And actually there's a series of very large glaciations. We find evidence for glaciation on all of the continents, apart from Antarctica, which is covered in ice, so that's difficult. But probably it's in Antarctica as well. So there are some big glaciations here that are sometimes called snowball glaciations because some geologists argue that the glaciation went into the tropics. Sea ice came down from the poles to the tropics. Maybe even almost covered the entire planet. And this happens again. And it coincides with another rise of oxygen, the second rise here, up to levels that we don't know exactly, but maybe several. There's certainly more than 5%, probably 10%. And something else happens here, which is the appearance of animal fossils in abundance. So the oldest, there are some creatures called the Ediacaran biota. And 575 million years ago, if you go to Newfoundland, a place called Mistaken Point in Canada, there are these impressions. They look like big leaves, but they couldn't have been plants because they were living under deep water, you can tell from the geology. So we think they were very simple animals. They had no eyes, they had no legs, they just looked like a pizza. Okay? Some of them really do look a lot like pizza. They're bumpy and they're round. With a thin skin, they could get nutrients through their skin directly. No mouth, no anus. Very important for modern animals. The Ediacarans, well, they were kind of an experiment, like a distant cousin. They died out. And then later, 541 million years ago, is the beginning of the Cambrian period. And there's a period of 10 to 30 million years when lots of new body plans, architectures of animals appear. That's called the Cambrian explosion. Not much of an explosion. I mean, spread over 30 million years, but that's the name. And then very familiar animals appear then. And also, maybe a little bit before that, there are animals with what we call bilateral symmetry, like me, symmetric on roughly. So these are our ancestors. The bilaterians appear maybe something like 550 million years ago, the first bilaterians, bilateral symmetric animals. There's actually a third rise. About 400 million years ago, something else happened. Well, just before then, you find the first fossils of plants, leaves. And then lots of plants on the land and trees. And this caused a third rise of oxygen about 400 million years ago. Some other biology happens then. Large predatory fish appear in the ocean, perhaps because there was more oxygen, could support these big, mean, nasty fish, big teeth. And about 300 million years ago, there was a bump in the Carboniferous, we think, where oxygen was perhaps higher than it is today, maybe up to 30% instead of 21%. And there are some interesting things there in the fossil record. There are dragonflies, this big, spiders. You think you've seen a big spider? No, they're big spiders in the Carboniferous. Well, insects don't have lungs, they have little holes on the side of them. They're called spiracles. So they rely on diffusion of so the oxygen comes through the holes and diffuses directly into the animal. And it's very difficult to be a big insect, this big, or an arachnid, unless you have more oxygen. So the geochemistry is consistent with the biology. It was also possible to be a giant dragonfly because something was missing from that world that we have today. Birds. Okay, so there was a niche that could be filled. I think if birds had been around, no giant insects, they would eat them before they had time. The source of oxygen, of course, is photosynthesis, which you can simplify to this equation. Carbon dioxide and water makes organic matter, simplified as a carbohydrate. Carbon, water, carbohydrate, and oxygen. But this can go the other way. An apple plus oxygen is respired back again to H2O and CO2. So the net source of oxygen we think of as when this gets buried into sediments and separated from the oxygen. Then the oxygen could go into the atmosphere, but it can also be lost to various other reactions. But essentially the net source of oxygen on geological timescales is the same as the burial flux of organic carbon. So it's something we can actually trace from the geochemistry. And I've suggested that the time history of oxygen levels may be related to the tempo of biological evolution. High levels of oxygen are necessary for us. If you don't believe me, put a plastic bag over your head. For several minutes, you'll find a problem. And the ozone layer screens out the land, as I mentioned before, and allows large life to exist on land. So when we think about other complex beings in the cosmos, well, there's only one periodic table. There's only elements do certain things, and, well, you could have, what about fluorine? That's more of an oxidant than oxygen, or chlorine. Well, the problem is fluorine explodes with organic matter, which I think wouldn't work very well. And chlorine, as you know, is used to clean, because it's a bleach. It destroys organic matter as well. Too reactive. Oxygen is almost too reactive. I mean, it can kill you if you have too much of it, but it's intermediate. So it's stable enough that it can accumulate in an atmosphere. I don't think fluorine or chlorine ever could in abundance because they're so reactive. They react and would form solid minerals. But it provides a lot of energy, this molecule, and allows us to run and jump and think. And it would allow other creatures on other worlds to run and jump and think too, if they use an aerobic metabolism. So what determined this length of time? Why was there a boring billion? Why wasn't it just cut that stuff out and go straight to the exciting things? Why did it take so long? Would it take as long on another planet? Would it take longer? Would the planet just have something wrong with it that makes it never get a lot of oxygen and it's stuck in a boring 10 billion? So it never develops complex life. These are issues of the details of the chemistry of a planet and the way that it interacts with the biology, which we don't fully understand because we don't fully understand the Earth.
Sorry, everything you say, if I have to look for a life indicator in an exoplanet,
Yeah.
ozone is better than oxygen, no?
You need oxygen to make the ozone.
Or you need both?
Because remember, you break up an O2 molecule, you need to get an oxygen atom, and then an oxygen atom plus an O2 molecule combined to make ozone. So no oxygen, no ozone. Ozone is just a proxy that there's a lot of oxygen there, O2. Atmospheric escape is also very important for the way that, so does anybody have any questions about this first part of my talk, which was about the effect of biology on an atmosphere? Or does anybody want to disagree with me? This last bit was a little speculative, but I sounded pretty convincing to myself.
Question.
Yeah.
Was there enough ozone at that time?
Yeah, so at this point, when you've got maybe 1% or a fraction of a percent, we don't know exactly this level, somewhere probably between 0.2 to 2% absolute level of oxygen. This is enough for a pretty good ozone layer. It wouldn't be quite as thick as today, but within a factor of 3 or 4 or something, because it's non-linear. So as you go from these small values up to these values, there's a big increase in the ozone. And then as you go from here up further, it doesn't increase so much. Yeah. So the ozone layer is from here, goes back to about 2.4 billion years ago. Yes?
About the nitrogen fixation, you said you can return to the slide?
Yeah, I said that the nitrogen might have been lower in this period of Earth
Okay,
history.
I would like to know if the atmosphere was as rich in nitrogen as it is right now.
Well,
How many nitrogen there was?
okay. So at the moment, not much has been published on this issue. But I was an author on a paper 2 years ago, 2012, in Nature. And what we did, this is is an amusing technique, but we looked at fossil raindrop imprints. So when it rains, the drops can make a little hole, a little crater, and sometimes, if you're lucky, you know, that might be covered in a volcanic ash or something. And then you have a fossil raindrop imprint. And the oldest ones in the world are 2.7 billion years old. And actually, there's two sets. There's some in South Africa and some in Australia. But anyway, the good ones are the ones in South Africa. And we thought, well, maybe we could use this to measure the air density at the time. Because if the air density is less, the terminal velocity would be bigger. They make bigger craters. Okay? Okay, but then it's complicated because it depends on the substrate, and maybe this is not going to work. But then it turns out that nature is kind to us. That there's a maximum size of raindrop that only depends on gravity and surface tension of water. And it's a sphere equivalent diameter of about 7 millimeters. And it doesn't matter, you could have a thicker atmosphere or thinner atmosphere, that wouldn't change. The biggest raindrop would always be about 7 millimeters possible, because then it breaks up, the surface tension is overcome. So we can look at the biggest one, biggest raindrop crater, and we did some calibration experiments with drops into ash, the same substrate. And we worked out that the surface pressure in this place where we had the drops was less than 0.5 to 1.1 atmospheres. Okay? We have a big error bar. It's not the very precise technique. So we did another technique. We haven't published it yet, but a manuscript is written. And what we did was we found some ancient lava flows, thin ones. When a volcano gives out a lava flow, it solidifies from the bottom and the top first. So it goes solid. But in certain types of lava, there are bubbles. So the gas comes out and forms a bubble. And if you look, you'll find small bubbles here and big ones here. So why is that? And the answer is, here the pressure is the atmosphere, and here the pressure is the atmosphere plus the pressure of the solid material. Okay? Call that P lava. So if you measure the size of these bubbles, the volume, and measure these ones at the top and the bottom, write down some equations. Simple, it's just the gas laws. Then you can figure out the pressure of the atmosphere. So we've done that for some 2.7 billion year lava flows, which were erupted on a beach, which was lucky, because we know it's sea level. And then I think we get something less than so this bit's not published, this lava flow stuff, but hopefully it will be soon. So we find that the total pressure was less, and so the nitrogen has to be less. But to us it makes sense because there's no oxygen, hardly any oxygen in this atmosphere. And so a lot of nitrogen can be in the form of ammonium, even in the ocean, instead of nitrate. So the hydrogenated form, not the oxidized form. And then it can find its way more easily into minerals. And so it can be lost. And so you end up with probably not so much nitrogen. But then nitrogen would rise with oxygen. Maybe nitrogen was higher in this period. Maybe that's why there's no cold spells, no glaciation. I don't know. We don't know what the nitrogen level was here. In this period of Earth history, it was probably about the same as today. There's some subtle geochemical evidence you can look at. But anyway, that's why I think it was lower. So it was a fun project to look at these raindrop imprints in South Africa and these lava flows. These were from Australia. So there's in northwest Australia and in South Africa, there are good sedimentary rocks from the early Earth, which range in age from 3.5 billion years old to something like 2.5 billion years old. So good sedimentary rocks from the Archean. And you can study them and you can figure things out, you can work things out about the ancient Earth. And there's probably a lot more that could be done, but it just depends on your imagination. So the next topic I'm going to discuss is atmospheric escape. Ways to lose an atmosphere or change its chemistry. And there are three basic ways. One is that if the molecules are hot enough, they can evaporate. And when they evaporate, one at a time, we call it Jeans escape. Okay? Named after James Jeans, the astronomer. When the upper atmosphere has a lot of ultraviolet light, extreme ultraviolet light from the young sun or another star, if we imagine another planet, the whole atmosphere can heat up and it can go out into space in a way that's like the solar wind going out from the sun into space. So the whole atmosphere is going out, and we call that hydrodynamic escape. And it can, maybe this is a hydrogen-rich atmosphere, but it also drags along other gases. Then there's non-thermal escape. This could be due to interaction with the solar wind particles, sputtering. It can be when you have an ion which is trapped around a magnetic field line. It can collide and become a neutral particle, and then it's no longer, may have attained a velocity, ready to escape, but it's no longer bound to the magnetic field. But the magnetic field of a planet is not always closed. At the poles, there are open field lines, and you can escape along the open field lines, and that's called a polar wind. This is charge exchange, charged particle. No, this is, reactions. Sorry, this is something different. This is a chemical reaction where an oxygen, which is charged, reacts with an electron and can make fast oxygen atoms. So these are not bound to the magnetic field, but they can be fast, they can escape. And this is not a very good diagram, doesn't come out very well, but this is impact erosion. So you have an impactor, and it hits an atmosphere, and it can escape a cone. All of this cone can be eroded away and be lost. And if the impact is bigger, the cone is bigger, and it can even extend to a whole tangent. Everything above this tangent can escape for the case of really big impactors. So these are the three ways that atmosphere escape: thermal escape, non-thermal, and impact erosion. Now the big ways to get rid of an atmosphere are this one, hydrodynamic escape. That can erode a lot of atmosphere. People talk about this for exoplanets, if they're close to the star and they have a hydrogen-rich atmosphere, and maybe the planet is somewhat small, then hydrodynamic escape can essentially evaporate the atmosphere and leave nothing behind, potentially. And impact erosion. If you're close to a star, you have a fast Keplerian velocity, and you tend to have faster impacts. So more kinetic energy goes with the square of the velocity, and that can be more efficient at the erosion. But the hydrodynamic escape depends upon the ultraviolet, particularly the extreme ultraviolet and far ultraviolet, and maybe in some cases the visible spectrum as well, which heats and expands the air, pushing it upwards, accelerating, and hydrogen-rich atmospheres on rocky planets can undergo this form of escape. And I wrote an article about this for Scientific American, which I think is translated. There's a Brazilian version.
Yes.
Yeah. So there is a Brazilian version of this article somewhere, which is where these pictures come from. In Gene's escape, this happens today. So hydrogen escapes from the Earth by Gene's escape, partly, also some non-thermal escape. But what happens here, the average velocity of hydrogen atoms at the exobase, the base of the exosphere of the Earth, is only about 4 or 5 kilometers a second. What's the escape velocity for the Earth? It's about 11, or maybe at that altitude, 10.8 kilometers a second. But hydrogen escapes. And the reason it escapes is because it has a big tail, which is above the escape velocity. So in the Maxwellian velocity distribution, even though the average velocity may be less than the escape velocity, particles can still escape. And they escape from the exobase, which is where the atmosphere joins space and it becomes collisionless. So if you have an escape velocity, you're up here and you're directed outwards, or your velocity vector directed outwards is bigger than the escape velocity, the particle escapes. There's effectively no more collisions at this level. Down here, the hydrogen has to diffuse through the other gas from the homopause level. So this up here, there's diffusion dominated. Down here is turbulence dominated. So mixed, but not well mixed. Hydrogen diffuses through. So what actually sets the escape rate in the modern atmosphere is the time it takes to diffuse through here. That limits the rate that hydrogen can escape. Once it gets here, it's pretty easy to escape. And helium also escapes, not with Gene's escape, but through non-thermal escape, through the polar wind in particular. But it's light enough to escape. And the escape velocity is just when the kinetic energy is equal to the gravitational binding energy, solve for V. But this affects planets. So if there's a rule of thumb, which means a rough idea. If the Gene's escape applies to a molecular atom, if the mean thermal velocity exceeds 1/6 of the escape velocity. The mean thermal velocity depends upon the mass of the molecule. So we can do a plot, temperature of the exobase, the upper atmosphere, not the surface, although sometimes it's the surface for the moon because there is no atmosphere. And then 1/6 of the escape speed in kilometers a second. And so you can see that this line means everything above this line, hydrogen won't escape from by Gene's escape. This only applies to Gene's escape. So the giant planets, hydrogen cannot escape. In principle, it can't escape from Venus, but it does because there's non-thermal escape mechanisms, such as the solar wind and so on. Mars is here, so in principle, things like water vapor, ammonia and methane are able to escape from Mars. And then the moon even something which is inefficient, like genes escape, more or less every molecule you can think of can escape from the moon by this inefficient mechanism. Hydrodynamic escape has similar mathematics in its physics to the solar wind, except in the solar wind it's charged particles, ions, and electrons. And there's a magnetic field associated with the solar wind, but not in a planetary wind, which is another way to say hydrodynamic escape. Hydrogen, usually it's the hydrogen that's undergoing this process. It pushes heavy atoms out with it, but the heavy atoms also fall down under gravity. So there is some mass fractionation. So if we look at the chemistry of isotopes, we look at the isotope ratios on Venus, Earth, and Mars, we can perhaps see if there's some evidence for hydrodynamic escape in the past. And potentially this can remove a lot of atmosphere. Genes escape is very inefficient. There would have been a good time for hydrodynamic escape on the early planets when there were steam atmospheres during accretion. And at this time there's very high extreme ultraviolet flux, so roughly below 100 nanometers wavelength or so. And is there evidence? Well, we can look at the noble gas isotopes. So the lighter isotope of neon would be dragged off in preference to a heavier isotope. So we should see a lower neon isotope ratio. This is the solar ratio. This is Earth's atmosphere. This is Mars. We don't know Mars very well. And Venus. So it suggests that even on the Earth and Venus, there might have been hydrodynamic escape, and also on Mars. But that would have been on the very early atmospheres. Is there evidence in general for thermal escape? So here I've got a plot of relative stellar heating. This is the sun, unity. And this is 10 times, 100 times the sun, 1% of sunlight. And here's escape velocity. And here are some colorful objects, the giant planets, other ones in our solar system, some extrasolar planets, and over here are some rather sickly looking objects. The ones in gray, they're empty, colorless. I don't like these, they have no atmosphere as an atmospheric scientist. But these are the colorful ones that have atmospheres. And there's a dividing line which you could draw. It's a little arbitrary. But you'll see that the ones with a big escape velocity and less relative solar heating, that favors atmospheres. But if you're on the wrong side of the Berlin Wall, then you will lack an atmosphere, like these small objects, the moon, or Mercury, or some of these asteroids, or COAA 7b, which is an extrasolar planet, very close and very hot with respect to its parent star. So as we get more exoplanets, we could plot them on this kind of plot, and we could probably make an estimate of, is it going to have an atmosphere or not? A binary question. Has an atmosphere, doesn't have an atmosphere. And this may not be the perfect thing to plot because it depends upon the spectrum, not the total solar flux, but it's a guide. This is an ultraviolet image of the Earth at 121 nanometers, which is also known as the Lyman alpha line of the hydrogen atom. So what's happening here is sunlight at this wavelength is being absorbed and then re-emitted from these hydrogen atoms. These are hydrogen atoms, this red stuff. And what we're seeing here is a halo, a glow of hydrogen atoms around the Earth today. So hydrogen is escaping from the Earth today. It's not very fast, not much. But in the past, it would have been easier for things like methane to accumulate in the atmosphere, and methane also gets photolyzed and the hydrogen escapes. So in the past, the hydrogen escape flux would have been larger, maybe thousands of times larger, because there would have been 1,000 times more hydrogen atoms in the upper atmosphere from the reducing gases, not from water vapor. That's still still a problem because it forms clouds, but from the reducing gases. Well, in chemistry, when you add hydrogen to something, you do the process of reduction, or you reduce that chemical. You hydrogenate it. When you pull the hydrogen off, you oxidize the something. So if the Earth loses hydrogen, the Earth oxidizes as a whole. We draw a box. This is a box model. I'm putting a box around the Earth. As hydrogen comes out of the box is oxidized. That's the Earth, the whole planet. So with a lot of hydrogen escape in the past, the Earth would have been oxidizing slowly but surely. And this could be important for planetary evolution. It could be the reason why it took a long time for oxygen to rise, because the Earth was slowly oxidizing and eventually reached a tipping point where oxygen could flood the atmosphere. That's one theory.
So if you're losing hydrogen atoms, they're coming from either methane or water.
So today, in this picture of the modern Earth, half of these hydrogen atoms are coming from methane.
They are. But in the past, they would have been still from methane, is it?
Yeah, so in the Archean atmosphere, if you've got 1,000, 2,000, 3,000 parts per million of methane, virtually all of, if we did this in the Archean, virtually all of the atoms here would be from methane.
Okay, so it's not water, because water's mostly in the liquid form
and clouds.
And clouds. And it's,
yeah. But it doesn't matter for the chemistry. If you take hydrogen away, you're still oxidizing the planet.
mm-hmm. And the question is, what happens to that carbon and then oxygen, right?
Well, the carbon doesn't go, it stays.
Mm-hmm.
But the planet as a whole has been oxidized. And we can sometimes see this visually. Here's the moon. It's gray colored. Here's Mars. It's red, orange. On Mars we have iron oxides, things like hematite, minerals like hematite, goethite, that are red colored. And that's why when you look at Mars in the night sky, it's red. But this, you can say the reason is iron oxides, but the ultimate reason is hydrogen escape. Water has been split, in this case it's water probably, that has been split, the hydrogen has escaped, and the planet's surface has oxidized. Now look at the moon, it's not red. Iron oxide's not there. Didn't have water and hydrogen escape, no oxidation. Here's the Earth, this is Australia, the Australian desert is red. You could look at Arizona, lots of deserts are red because there's iron oxides here. So this planet also oxidized and built up oxygen. Venus, maybe, we don't know really the surface color of Venus, but there's some spectral information to suggest that there are Fe3+, meaning oxidized iron-bearing minerals on the surface of Venus, which suggests hydrogen escape and oxidation of the surface of Venus. If it didn't have the oxidation, it would be dark and basaltic. This is a bit uncertain because we don't have such good information from the surface of Venus. But sometimes, you can just tell from looking at the planet, Mars is red, it had hydrogen escape, it oxidized. Now the third kind of atmospheric escape was the impact erosion. So let's plot a median impact velocity, which we get from dynamical models of the solar system, divided by the escape velocity, against the escape velocity. And you'll see that the colorful objects, the ones I like with atmospheres, are down here. They're safe from impact erosion because the impact speed is small relative to the escape velocity. Less than, I've drawn a line here at 5. It's somewhat arbitrary, but that seems to be the dividing line. Whereas these objects up here, Mercury, Ganymede, here's an interesting pair. Ganymede, the largest moon of Jupiter, Titan, the largest moon of Saturn. They're about the same size. But Ganymede sits in a big gravitational potential well of Jupiter. Titan doesn't. It orbits a smaller planet. So Ganymede suffers a bigger impact speed than Titan. And that puts Ganymede on this side of the line where it's prone to impact erosion of an atmosphere. So if Ganymede had an atmosphere, it could have lost it perhaps by impact erosion. Whereas Titan wouldn't. It would probably, on average, gain volatiles rather than lose them. There are 2 Mars here. There's only 1 Mars in our solar system, but this is Mars for long period comets if it's hit by an Oort cloud comet. This is Mars if it's a body that hits it in a disk that's coming from the plane of the disk. So Mars is, whether Mars is prone to lose its atmosphere or not depends in part on what kind of body hits it. But I think on this diagram, Titan and Ganymede are the most telling objects because they're about the same size and the same mass, but different regimes of impact erosion. And we could actually do this for extrasolar planets if you can estimate the impact velocity. And that will also tell you which exoplanets are prone to impact erosion at their atmospheres. So for example, a lot of people, did you mention M-stars this morning? Yeah, a lot of people talk about planets around M-stars because they're easier to detect in some ways. But they're close to their star and they will have big Keplerian velocities, and some of them might have big impact velocities. So it could be a problem for habitability of M-stars and habitable zone of M-stars. And Mars, there's evidence that there was atmospheric loss from Mars. So we can look at the carbon dioxide on Mars. There's 6 millibars in the atmosphere. In the regolith, which is the broken up rocks and soil, estimates are less than 40 millibars. Caps, not very much. Subsurface, don't know. Depends how much is locked up into carbonate rocks. But there's not much carbon dioxide on Mars that we know about. Look at the ratio of the nitrogen to carbon dioxide for Mars, Venus, and Earth. For Venus and Earth, we take into account the carbon dioxide in the crust as carbonate rocks. For Mars, we assume there's very little, because we can't see it at least. And you see that it's similar, the ratio, but when you look at the volatile mass versus the planet mass, Mars is very depleted. So it could have lost these things with equal efficiency through impact erosion or through hydrodynamic escape. We can also look at the argon-40, argon-36 ratio. This isotope is primordial, and this one is produced continuously in radioactive decay from potassium. So this one builds up over time, whereas this one is at the beginning. And Mars has 10 times higher ratio than the Earth in its atmosphere. So that suggests it may have lost the 36 argon early on. Perhaps it was lost during impact erosion. And then models of impact erosion suggest that if Mars had a thick atmosphere, 100 times thicker than it today, so it'd be like 1 bar instead of 10 millibars, then it could have been depleted by a factor of 100 during heavy bombardment during the early solar system. So that's a paper by Melosh and Vickery, where they have a sort of semi-analytic model of impact erosion. And some other authors, there's a review paper that looks at the effect of impacts on the early Martian climate. Since then, so there's a lot of damage that's done to Mars early on, but there's further damage that can be done to its atmosphere. Because it has no magnetic field to protect its atmosphere, then ions can be picked up by the solar wind. You can have charge exchange reactions which make ions, neutral particles, and they can flow out to space. There's photochemical reactions that happen on Mars to produce fast nitrogen atoms, fast carbon atoms, fast oxygen atoms. So unlike the Earth, where carbon, oxygen, and nitrogen are bound, they don't escape. On Mars, these atoms do escape. And there's evidence looking at isotope ratios that nitrogen has escaped compared to the Earth because the lighter isotope is enriched. And the models suggest since about 4 billion years ago, the atmosphere has been thinned out by 50 to 90% on Mars. That's after it's already been thinned out by impact erosion. So this is why when we look at Mars today, we see a thin atmosphere. It's a small planet, and it couldn't hold on to its atmosphere. And I might skip this table, but there's a whole bunch of isotopes you can look at. And I mentioned the nitrogen, the neon, the argon, and you can think about what that means and interpret it in terms of escape processes. These are other primordial isotopes of argon and xenon also. But the picture that I sort of have is maybe that if it had a thick atmosphere early on, who knows how thick it was, there are processes that can rapidly deplete that atmosphere by a factor of 100 and then by another factor of 10 in the last 4 billion years. So size is important. You need something bigger than Mars, really, to be habitable, because you can lose an atmosphere if you're as small as Mars. Where is that transition? Mars is 1/9 the mass of the Earth. Is it half the mass of the Earth? We don't really know, but somewhere between Mars and the Earth. So that's part 2 of my talk. So does anybody have any questions about what I just talked about, the topic of atmospheric escape? Yes?
There's water on the surface of Mars throughout, even beyond the point where you had the suggested dramatic 2-order magnitude loss of atmosphere, right?
Yes.
So is the 60 millibars enough to keep water?
Well, there's a large literature on, on this topic. So when you look at the surface of Mars, you see these dried up valleys, and there are many of them on the old cratered highlands, literally hundreds of valleys. And then there's another feature you see, which are giant channels. So a valley has tributaries, looks like what we call dendritic, finger-like sources that come in to feed a river, much like the Amazon or something. Whereas a channel is a single path for a large body of water, like a flood that goes down a channel, and that's it. So we see signs of flood channels, which are thought to be somewhat later in history. And then on early Mars, about 3.7, before 3.7 billion years ago, we see lots of valley networks, which were clearly in some cases cut by, many cases cut by liquid water. So how did that happen? And there are various hypotheses about that. One is that Mars somehow had a thicker atmosphere at that point, and it was warm enough to maintain the liquid water. Another theory is that there are lots of temporary climates. For example, the impacts themselves, the smaller ones, can melt water and create a warm atmosphere temporarily. You could do that thousands of times and cut valleys. That's what Brian Toon, who I mentioned this 2 Natal review paper, he favors that hypothesis. But other people vehemently oppose that hypothesis and don't think it can explain all of the geology that we see. When you get beyond this era of the valley networks, so roughly the dividing time would be roughly 3.7 billion years ago. After that, there are very few valley networks, and the rate of erosion is very small. So it's like there was a change, that it went from an environment that had liquid water on the surface to dry. And in the last 3 billion years, not a lot. Mars has probably been quite similar to today. About between 3.7 and 3 billion years ago, these giant flood channels appeared. And the theory for those is that it was driven by geology, because in that case, they come from places such as canyons. That's the source of these channels. And you needed some geothermal heating to melt ice in the subsurface and release a big flood. So the theory is that that's driven by subsurface heat.
And that would still stay, that could last for long enough to show the feature even if the atmosphere is only...
Maybe.
Maybe,
yeah.
It's tricky. Okay.
It's tricky, yeah.
Okay.
And there's also another confusion with the channels, which is some of them also have lava in the base of them. So it's a mix of, and some people argue that the lava can be runny, inviscid, and can also widen a channel. So it could be a mix of some lava-cut channels and some water-cut channels. We find lava-cut channels on Venus and on the Moon and maybe Mercury. So they're quite common, and you shouldn't exclude them entirely from Mars. But I think there is evidence in the isotopes for atmospheric loss. How and when exactly it happened is still an issue of research. Any more questions? If not, then the next thing was climate. So how did climates evolve? And I need to talk a little bit about the Earth's climate. So I talked about, in the first lecture, the fundamentals, that we have solar flux and albedo of the planet, and it determines an effective temperature, even in the absence of an atmosphere, okay, in equilibrium. But then you have a greenhouse effect due to the atmosphere that's added on. So for the Earth, this was 255 Kelvin, this effective temperature. And then there's a greenhouse effect of about 33 Kelvin, which raises up the mean global temperature to 288 Kelvin. Okay? 255 plus 33 equals a surface temperature of 288. And on the Earth, this greenhouse effect is 33 Kelvin. Mars, it's somewhere between 5 and 7. Venus, it's about 507. So you can remember that the greenhouse effect on Venus is about 500 Kelvin bigger than on Mars. This is a pie chart showing you the contributions of the gases and clouds to the greenhouse effect on Earth. So the biggest greenhouse gas is water vapor. It accounts for 50% of this. Clouds, ice clouds can act as a greenhouse. They let through the visible light. They trap sort of the infrared. So about 20% of the greenhouse comes from clouds, 20% from carbon dioxide, and these other gases are down at the 10% level. However, water vapor cannot accumulate indefinitely because it rains and it snows and they form clouds. So this is a condensable species. This is not. Carbon dioxide, as you know, doesn't condense on the Earth. And so as this goes up, then the water vapor goes up because it's warmer. If the air is warmer, you hold more water vapor. So the water vapor is a positive feedback on climate. If it gets hotter, more water vapor, it makes the climate hotter. Positive feedback. And what it means is that for an increase in CO2, if you just took into account the infrared effect of CO2, you have to double that, because when you take into account the feedback from water vapor. Another positive feedback is ice albedo. If the ice sheet grows on the poles, it reflects more sunlight. The Earth cools, makes more ice. More reflection, more ice. So it makes it colder and colder, a positive feedback. That's how the Earth may have had a snowball Earth at some point, because the ice caps grew so big that there was a positive feedback. But it operates in reverse. So if the Earth gets hot, the ice sheet gets smaller, there's less sunlight reflected, space, more absorbed, so the Earth gets hotter and hotter, smaller ice sheets. And that's something a bit like today in global warming, where Greenland ice is melting, which makes it hotter, which means Greenland will melt more. But there have to be negative feedbacks that stabilize the system. One is very simple. If the Earth gets hotter, there's more outgoing radiation and the Earth cools. And then in the long term, in the long term, there's a cycle called the carbonate-silicate cycle that operates over 1 million years or so, which stabilizes the climate. And I think I've got a slide in that later. But this long-term thing is thought to be largely responsible for the climate stability of the Earth for most of Earth history. And the atmosphere had to be different in the past because solar luminosity has increased over time from 4 billion years ago to present. There have been these changes, the origin of life, different forms of life, the rise of oxygen, the rise of animals. But broadly speaking, for most of this Earth history, the ice has not been covered in, the Earth has not been covered in ice. And the way the carbonate-silicate cycle works is that carbon dioxide, if it gets too high on long time scales, it will react with rocks. This is a silicate on the land. The rock dissolves, it goes into the ocean, and the carbon dioxide gets locked up in limestone, calcium carbonate. And so the CO2 amount goes down. If it's hot, there's more rain, usually. There's warmer temperatures, which enhance the speed of this reaction. So it's a negative feedback. The hotter it is, the faster you remove the CO2. If it's too cold, then this slows down. And so the CO2 level tends to reach some moderate level that keeps the Earth warm, not too hot, not too cold. Of course, if this was all that were happening, we would lose the CO2 potentially, but it gets recycled when the plate when limestone is subducted. It can get heated up, and the CO2 comes out again. We have planets where this system doesn't work. So Venus, there's no liquid water here, so it doesn't rain. The carbon dioxide in the atmosphere of Venus doesn't react with the surface as carbonic acid, which is what CO2 plus water produces, a weak acid. So Venus can't get rid of its carbon dioxide. It's stuck in the air. And any volcanic carbon dioxide would have accumulated. And on Mars, it doesn't have active volcanoes. There's no volcano on Mars today that's active, that's been detected. No volcanic gas coming out. So if CO2 has been lost to space, or it's been lost to the surface, there's nothing to put it back. There's no volcanic gas on Mars. So Mars is stuck in a sort of permanent ice age. It's very cold at the surface of Mars. Venus is stuck in a permanent hell. This is time in billions of years. This is temperature, effective temperature. And if we had the present atmosphere, we would go below the freezing point of water 2 billion years ago. This difference here between the effective temperature and the actual temperature, that's 33 Kelvin. That's the current magnitude of the greenhouse effect. So in the past, we know that the planet was not covered in ice constantly, so it means the greenhouse effect must have been bigger in the past. That means a different atmosphere with more greenhouse gas. And that can be satisfied in the Archean because we had a lot of methane, which is a greenhouse gas, and maybe more carbon dioxide too, maybe between 50 and 100 times more in the Archean are the estimates. The system can also break. This is a negative feedback. Surface temperature goes up. You get more outgoing infrared flux. More outgoing infrared flux cools the surface. This gets broken in the runaway greenhouse effect, right? Because in the runaway greenhouse effect, surface temperature goes up, but outgoing infrared radiation stays the same because it's set by the properties of water vapor. And this limit on outgoing infrared in a saturated atmosphere of water vapor for the modern Earth is something like 300 watts per square meter. But it's okay. We're far enough from the sun that the average incoming solar flux is less than this limit. But if we moved the Earth, like I mentioned the other day, closer to the sun, then this shows you that, well, basically, let's look at this. The surface temperature would go up and up and up, and then you'd reach, this is the outgoing flux, you'd reach this plateau, the runaway greenhouse limit, roughly when the surface temperature is almost 100 degrees Celsius. And then the Earth's surface temperature just keeps increasing and increasing because it's getting more sunlight energy than is going out. And then it melts here. And then it begins to lose energy and come back into balance. In a diagrammatic form, here's the modern Earth, 15 degrees Celsius mean global temperature, very dry upper atmosphere, little hydrogen escape, the ocean is safe. If we get close to the runaway limit, we have a very moist atmosphere. Instead of 4 parts per million, we have 20% all the way up to 100 kilometers. And water vapor can be destroyed, and this ocean can be destroyed relatively quickly. If you then have a full runaway greenhouse effect, there's no ocean. All of the ocean goes into the air. This is an atmosphere made of water vapor, mainly. The other gases are not very important, and you lose the ocean. This is what we think happened to early Venus, but it may have transitioned from something like the Earth to a warm planet, still had an ocean. And the question is, how long did this take? Was there an early Venus that was habitable? Did we come from Venus? Are we Venusians? And there are there's another possibility that Venus, this is wrong, that Venus didn't have an ocean, it just started out dry, that we're deceiving ourselves. But I don't think that's right, because the carbon dioxide and nitrogen amounts are similar to Earth, what we can see in the Venusian atmosphere. And we know that water is delivered the same way, right? With the same form of impact accretion. So it seems reasonable that Venus did have considerable water. And all of this carbon must have been oxidized somehow, so that would have come to make carbon dioxide from the water. And the main question is whether Venus had an immediate impact-induced runaway steam greenhouse, so at the beginning it never was habitable, or whether there was a period, 100 million years, half a billion years, a billion years, when Venus was a habitable planet. So, to summarize then, we have 3 planets, Earth, Venus, and Mars. Earth, inhabited, in the right place in the solar system, the right size to recycle volatiles through plate tectonics. But life has changed the atmosphere. Every gas, major gas with the exception of argon, is modulated by biology. And the largest change was the rise of oxygen 2.4 billion years ago. Changed the color of the planet, changed the nature of life on the planet. But luckily, habitability has been maintained by feedback processes, a mixture of biology and geology. Venus was it just grew up in a bad neighborhood, so to speak. Its position meant that a runaway was inevitable at some point if it had a lot of liquid water on its surface, which we think it did. So the hydrogen was lost. It probably dragged away a lot of oxygen also, but oxygen also would have reacted with chemicals on the surface. And so Venus now has a thick atmosphere and is dead, paradoxically, because of escape, the selective loss of the water. And then there's this question, was there life on early Venus? Don't know. How do we find out? Difficult, given the nature of Venus. Mars has a thin atmosphere today because there are processes that lead to bulk loss of all the gases at the same time of the original atmosphere. There's impact erosion and hydrodynamic escape. Mars has lost water, it has oxidized, it's turned red due to selective escape of hydrogen compared to oxygen. However, there was this early period when it appears to have had a thicker atmosphere, liquid water on the surface. So there's still a question, just as for Venus, was there once life on early Mars? Was there once life on early Venus? Mars is easier, we can send spacecraft there, we don't have to design something extreme. But remember, Venus, early Venus could have been more habitable than early Mars, because it may have had an ocean. Whereas people talk about an ocean on early Mars, but there's not very good evidence for it, really. It's speculation. So that's the end of my lecture, and I'm happy to take questions.